Welcome back, folks. So in our previous pre-work, we looked at an introduction to logarithms, and I left you looking at a few questions. Question number 12 there, where I was asking you to try to come up with some properties on your own. I really think that that's a helpful way to learn these properties, is just to do some exploring. My hope is that we learn the following properties, and if you didn't get them, that's okay. Go ahead and after I give you these properties, go back and try to give another shot at number 12 if you didn't feel like you understood it. So let's go ahead and look at the first property. The first property says if we have the log base a of a, that's just equal to 1. To be honest, although I'm calling it a property, that's kind of generous, because that's just saying a to what power is 1. Or sorry, a to what power is a? And the answer to that question is a to the first power equals a. So the log base a of a is the number 1. But you can think of that as a property. Similarly, for b, we would have that the log base a of 1 is equal to 0. Why? Because this expression right here says a to what power equals the number 1. And the answer is a to the 0th power equals 1. So the log base a of 1 is 0. The other two identities are a little bit more complicated, and they'll be ones that you use often. They're actually what make logarithms such powerful tools. The other two identities are the inverse identities, and one of them would be that if we have a to the log base a of a number m, that is just that number m. So the way you can think about it is this is very similar to if I take the cube root of x cubed, that the cubing operation and the principal real valued cube root, those are just inverse operations of each other, and we arrive at just the number x. So some students like to say that the cube root and the cubing operation canceled one another out to arrive at just x. This one doesn't quite roll off the tongue, but it's the same result, that when we take the log base a of m and then exponentiate that result, we're back to just the number m. The other property is similar. It's just what we're going to do is we're going to have the logarithm on the outside and the exponent on the inside. So if we have log base a of a to the m, that's just equal to m. And my hope is that you saw that as you were exploring the questions that I asked you. But if you didn't, that's okay. This is sort of the reciprocal fact, or the opposite fact, where if I were to take the cube root of x and then cube that answer, I get back to just the number x. Taking the cube root and then cubing, it's as if those two operations, you could say, they cancel one another out. They undo one another, and we're just left with the original argument that we started with. Same thing here. I want you to think of logarithms and exponents as, in a way, undoing one another, leaving us with the original power. Okay, so we're going to practice using those properties here. I'm going to do the first one, you'll do the second one. So log base 3 of 3, that's this first property right here, that's going to simplify to be 1. Log base 3 of 1 says 3 to what power equals 1, and you can answer that question directly, or you could just go ahead and apply this part B here. Okay. Here we have the log base 3 of 3 to the 107th power. I don't even know if my calculator can compute 3 to the 107th power. That might be too big. Some calculators can do it, some can't. Okay? But then we'll take log base 3 of that, and what I need you to know is that these are inverse operations of one another. We're going to first exponentiate the number 107 over a base of 3, and then take the log base 3 of that number, and that just brings us back to the number 107. Now, I can't prove that to you very easily, or can't justify that very easily, but we could do something similar. So if I did log base 3 of 3 to the second power, what's 3 to the second power? 3 to the second power is 9. But log base 3 of 9 asks the question, 3 to what power equals 9? And the answer is 2. And you can see that we get back to where we started with. Okay? Here we're asked to find 3 to the log base 3 of 105. But again, that's this, and that's the other version of that inverse identity. And that says if we exponentiate a logarithm of the same base, we just get the power inside, or the value inside that logarithm. So this would give us minus, from that minus sign right there, 105. And if we clean up this whole mess, we get 108 minus 5. It simplifies to 3. It doesn't really matter what that simplifies to, but we got a chance to practice these 4 critical identities. So I'd like you to pause the video and try this on your own, and I'm not going to share in this video the answer to that question. So pause it and give it a shot. If you find yourself stuck, please reach out to me and be happy to help. Okay, we're continuing on in our exploration of logarithms. Here I ask you an interesting question. I ask you, what is the log base 2 of 20? And if you go back to that table that I had you fill out, you could try to answer the question from that table. But what do you notice? The number 20 doesn't show up on that table. But let's see if we can. So we're not going to have this. This isn't going to be a nice integer answer the way a lot of our other answers have been. But let's see if we can go ahead and answer the question anyway. So we know, for instance, that 2 to the 4th power is equal to 16. And we know that 2 to the 5th power is equal to 32. And we're being asked to find, in this question right here, the log base 2 of 20. That's asking the question, 2 to what power is equal to 20? And we would expect 20, that 20 fits between 16 and 32, so we'd expect our answer to be a number between 4 and 5. So let's just go ahead and identify that. We would expect 4 to be less than or equal to, actually strictly less than. I'm going to change that for your notes, folks. I'm going to change those to strictly less than. It's a true statement, but let's change it to strictly less than. 4 is less than the log base 2 of 20, because log base 2 of 20 is going to be, it's going to be larger than the number, so the exponent has to be larger than 4, but it has to be smaller than 5. So we know the answer should be somewhere between the integer 4 and the integer 5. Okay, the next question asks to use a calculator to evaluate 2 to the 4.5 power. So here I've pulled up a handy-dandy Desmos calculator, and we're being asked to evaluate 2 to the 4.5 power. And we get an answer of 22.63 rounded. So, oops, that needs to be brought up. So we just said that that was 22.63 after we round it to the nearest hundredth. Yes. So what are we saying here? Well, earlier on, in the first, we said we expect the log base 2 of 20 to be a number between 4 and 5. Now we can get this a little bit closer. We know that the number now needs to be between 4 log base 2 of 20, and because this value, 2 to the 4.5, is already bigger than 20, it's 22.63, we expect this answer to be somewhere between 4 and 4.5. So what I'd like you to do is, with a calculator, I want you to just plug in exponents to try to guess the answer, and you'll get closer and closer. So pulling up my calculator here, we saw, okay, just as a reminder, 2 to the 4th was 16, that was too big. 2 to the 4.5, that was 22, so that's already bigger than 20, so our answer is somewhere between them. We could do 2 to the 4.25. We're a little bit closer to 20. Let's keep going. We could do 2 to the 4.3 power. A little bit closer, 2.35, too big. 2.34, pretty close. 2.33, 2.32. So maybe 2.8. That's pretty doggone close. 2.5. We've gotten pretty close to 4 to the 2 to the 4.325 is about 20. And in fact, when I did this a little more accurately, I went ahead and said that the answer was log base 2 of 20 is about 4.32. So what I'd like you to do is I'd like you to mimic this example that I just went through. I asked you the question, what is the log base 2 of 20? And first I identified that it would be between the integer 4 and the integer 5, because 2 to the 4th was 16, which was smaller than 20, and 2 to the 5th, which was 32, which was bigger than 20, and then we actually got a good decimal approximation as to what that number should be. So I'd like you to go ahead and give that a shot. Okay, so we've got a few more examples to look at. This is some special cases. I want to remind you that you all know to read the expression right here as the cube root of 64, and the index of that radical is stated right there to be 3. That's why you know to read it as the cube root. But what if I asked you about this expression right here? Well, you all know to read this as the square root. That is, in this case, the 2 is not written out, but it's implied. So we all know that the index of that radical is 2, even though that it's not stated. We're going to do the same thing. We're going to have some implied bases for our logarithms, and that's a little bit confusing. So here's an exponential fact. 10 squared is equal to 100. 10 squared is equal to 100. You'd expect then, based on what we've taught you about logarithms, and you're 100% right, to assume this is how you would write it. And I'm telling you, unfortunately, it's not. You'd be 100% right to assume that we're going to say that the log base 10 of 100 is equal to 2. However, instead of writing log base 10 of 100, we're just going to write log of 100. The log base 10, it's implied, the log base 10 of 100 is equal to 2. So we're going to write it this way. So again, we don't write the base 10. When our base is 10, we don't write it. We just say that the base 10 is implied. I think that's a little bit confusing, but you've seen that before, where for our square root, the index of 2 was implied. Here, for the log of 100, it's understood that that base, this is log base 10 of 100 is 2. And you should read this as log base 10 of 100 is 2. Okay. So I'd like you to go ahead and practice. How would you read this expression? And if you need to back up the video, please go ahead and do so. But I want you to write out, how would you read this expression? Write it out. Okay. Now, since e to the 0th power, here I'm using e as in Euler's number. E is approximately 2.71828, yada, it goes on, never repeating. E to the 0 is equal to 1. Okay? So we use the number e to stand for this base, which is an appropriate base for an exponent. You'd expect to write the equivalent logarithm this way. That is, for the exponential fact, e to the 0 equals 1, you'd expect to write it as the log base e of 1 is equal to 0. And your expectation, I mean, there's nothing wrong with that expectation, but that's not how we've decided to write it. So instead, we're going to write it as the natural log of 1 is equal to 0. So this is read as the natural log of 1. Okay? So go ahead and I'd like you to, how would you read this based on what I just said here? How would you read this expression right here? And what is the base of this particular logarithm? So pause the video and answer that.